Hello everybody, in this video we're going to cover section 16.4, free energy. This is going to be a big chapter for us. We're going to define Gibbs free energy and describes its relationship to spontaneity. We're going to calculate free energy change for a process using free energies of formation for its reactants and products. And we're going to calculate the free energy change for a process using enthalpies of formation and entropies for its reactants and products. I'm going to explain how temperature affects the spontaneity of some processes, and then we're going to relate the standard free energy changes to equilibrium constants. So, we know that we can determine spontaneity by figuring out the entropy change of the universe. But this is pretty difficult, and I think we've already alluded to that with our approximation where we have to find the reversible heat for the system, we have to find the reversible heat for the surroundings, and we have to make temperature measurements of everything. But this was all actually simplified by a guy by the name of Josiah Gibbs, and he proposed an alternate property capable of predicting spontaneity called the Gibbs free energy. All right. It is defined in terms of the system's enthalpy and entropy. All right. So we've seen from Hess's law that we can figure out enthalpy values. We can see that we can figure out entropy values. The important thing here is that all we need to know now is information about the system. Okay. We no longer have to consider the surroundings. We just need to know the difference for the system's enthalpy and the difference for the system's entropy, and then we can figure out the Gibbs free energy. Just like enthalpy and entropy, free energy is a state function, so it does not matter the path that something takes, only what its initial state and final state was. At constant temperature and pressure, the free energy change, delta G, can be expressed using this, where the change in Gibbs free energy is a change in enthalpy minus the temperature and the change of entropy. Remember that we've added these deltas here, so now we're talking about differences. All right. And it will have this same relationship with the entropy of the universe. Okay, so where spontaneous reactions had a positive change in the entropy of the universe, we're going to have a negative delta G. So negative delta G's are for spontaneous reactions. And as similarly, we're going to have a reverse relationship here. The entropy of the universe goes down. Delta G is positive. So when we have a positive delta G, it's a non-spontaneous reaction. And they're both going to be zero at equilibrium. Let's see how we can start with our approximation here and come up with delta G. So if we start with this thing here, the first law of thermodynamics requires that the Q surroundings is going to equal negative Q system, and at constant pressure, the Q system is going to equal delta H. So this expression can be rewritten as delta H over T. Okay. Multiplying both sides of this equation by T and rearranging yields this here. And we can see that this term now is related to the change in entropy of the universe, but it has the opposite sign. And that's where we come up with delta G. All right, it's going to be scaled by the temperature, but still its sign is going to change with the change of sign of the entropy of the universe. So why do we call it free energy change? The reason is because delta G may be interpreted as representing the difference between the energy produced by the process, that would be our change in enthalpy, and the energy lost to the surroundings, and that would be this T delta S term here. That means that this difference here and the energy that was produced and the energy that was lost is all the energy that's available or free to do useful work by the process. Okay, so If a process somehow could be made completely reversible, the delta G of that process would be the maximum amount of work that you would be able to get out of that process. Where W max refers to all types of work except for expansion, the pressure volume work. There's a little bit of subtlety that we're not getting into here once we have expansion work, where we actually have to take into account the pressure and volume of the surroundings still. But still, it would give us a sense we would need the delta G in order to figure out the maximum work that would be available in that situation as well. It just gets a little bit more complicated than that. Okay, hopefully I've convinced you guys of the usefulness of Gibbs free energy. Let's talk about how we go about calculating it. We can calculate a standard Gibbs free energy change from the standard enthalpy and standard entropy. Okay, so we saw how to calculate standard entropy last time. You can go back and review the section on thermochemistry or the homework notes that I put out to see how to calculate the standard enthalpy. And then we can just plug those values into this equation here, where now we have these little circles up here to indicate that these are under standard conditions. Now, here's the thing. The standard condition for the Gibbs free energy is not necessarily always going to be at that standard temperature. We can plug in our temperature value here and get the standard Gibbs free energy at different temperatures using this. We are making an approximation when we do that, where we're saying that these guys aren't going to change much at this new temperature from what they would be under standard conditions, but this is usually a valid approach. Now, if we do want to just know the Gibbs, the standard free energy of formation, if we do want to know the standard Gibbs free energy change at the standard temperature, we can do the exact same sort of thing that we were doing for enthalpy and entropy in this case. We can look up the standard free energy of formation values of the reactants and products involved in the reaction. And you're going to see these right along with the enthalpy and entropy values in that appendix in the back of our table. All right. This is going to be the free energy change that accompanies the formation of 1 mole of substance from its elements in their standard state. That's what the individual standard free energies of formations mean. And it's going to be, by definition, 0 for elemental substances in their standard states. So we're going to have the exact same thing that we were doing for enthalpy and entropy, where if we had this model reaction here, we're going to sum up their standard free energies of formations and weight them by their stoichiometric coefficients. We're going to do that for the products and the reactants, and then we're going to take the difference between those to get our change in Gibbs free energy. Once again, this is just like the Hess's law that we used to calculate the enthalpy. So if you want a little bit more review on that, you can go back and take a look at that section. I believe that was chapter 5 in the textbook. And here is a nice little example. Okay, if I have this reaction right here, I'm going to go look that up as the standard enthalpy of formation for gaseous water. All right. If I looked up the standard enthalpy change for gaseous liquid, I would have that value, but I want to reverse that reaction, right? I want to have the liquid on this side as one of the reactants. All right, so I make that negative there. I sum them together, and I get this overall reaction here, and you can see what the Gibbs free energy change would be for that, right? So we can think about this in terms of adding together reactions, or we can think of it in terms of actually looking up the different products and reactants and pumping them into this equation here. Ultimately, these two techniques are synonymous with one another. I find this one to be a little bit more useful because I'm just needing to look up these values in that table Where here I have to think a little bit more carefully about how I would go about adding together those different reactions. So let's look a little bit at the temperature dependence of spontaneity. And we're going to see that there are 4 possible scenarios. Okay? Because each one of these is a difference, right? They could be positive or they could be negative. Okay? So if I had a positive delta H and a positive delta S, I would have a scenario where there's going to be a critical temperature. Okay? And above that critical temperature, delta G is going to be negative, and the process will be spontaneous. And below that critical temperature, delta G is going to be positive, and the temperature would be non-spontaneous. Okay? If I had the scenario where both delta H and delta S were negative, I get the same scenario here. Okay, there's going to be a critical temperature, all right? And below that critical temperature, we're going to get a delta G that is negative and it's spontaneous. So now at low temperatures, we're getting a spontaneous reaction. And if delta G is above that critical temperature, it's going to be non-spontaneous. All right. The other scenarios we have is when delta H is negative and delta S is, delta S is positive, right? Well, in that scenario, there's no way where this could be negative, right? If this is negative and then I'm subtracting a positive value here, it's just going to get more negative. This means that at all temperatures, the process is going to be spontaneous. And you could use that same exact logic when you're talking about our last scenario here. If delta H is positive and delta S is negative, well, then I have a positive minus a negative, so this is just going to become more positive, and there will be no temperature at which this reaction or process will be spontaneous. I did in the homework solutions a pretty thorough derivation of that using inequalities, where we can actually figure out whether or not a temperature is what the critical temperature is going to be. But I do like this graphic here because I think it's pretty useful, where they're pretty much graphing out the temperature versus free energy for these different scenarios. And we can see that this would be the critical point. The temperature that corresponds with crossing this would be the chance where it would move from spontaneous to non-spontaneous. So we have a scenario down here where delta H is less than 0 and delta S is greater than 0, and we're always spontaneous. We're just always becoming more and more spontaneous as we increase the temperature. All right. We have the scenario where delta H is positive and delta S is negative, and we're always non-spontaneous. And then we have those 2 edge cases where they are both either positive or negative. And we can see that there will be a point where it's not spontaneous, it's not spontaneous, it's not spontaneous. And then at some temperature down here, it crosses that line, changes the sign of the free energy, and starts to become spontaneous. So if we linearize this equation and take a look at that, we can see how that works out and stuff. And again, I would take a look at my derivation where I actually use proper inequalities here to kind of derive what these temperatures are going to be and whether it has to be higher or lower than it. Okay, so we've seen that delta G allows us to determine spontaneity by knowing information only about a system. We've seen that we can calculate the standard Gibbs free energy change if we have a bunch of restrictions that everything's at 1 molar and 1 bar and stuff for a reaction by using something similar to our Hess's law that we did before. So both of those are really, really powerful conclusions. But delta G actually allows us to go a little bit further, What it allows us to do is to calculate even delta G for a reaction under non-standard conditions. And the way that we can do that is with this equation right here. So what we're going to do is we're going to start with our standard Gibbs free energy change for that reaction, and we're going to apply a little correction factor, which is R times T times the natural log of Q, our reaction quotient that we learned about in our equilibrium chapter. So this is going to allow us to calculate delta G when we don't have a pressure of 1 bar and we don't have concentrations of 1 molar. Now there is a couple of caveats to using this equation. First, the R gas constant we're going to be using is 8.314 joules per Kelvin per mole. So you're going to want to make sure you have the correct R value. T should be in Kelvin so that it cancels out here. All right. And then this whole term is going to then have units of joules per mole. And delta G, if you're looking it up in our table, has units of kilojoules per mole. So we're going to need to make a conversion where we can change this over to kilojoules per mole, and then we can actually sum them together with the proper units to get the delta G for the reaction. When we have an equilibrium situation, we get yet another really powerful outcome for delta G. So when delta G is 0, the forward and the reverse driving forces are equal, and this process occurs in both directions at the same rate. This is what we call equilibrium, right? So Q in that previous equation is now going to be K, and our standard Gibbs free energy and the Gibbs free energy change is going to be 0. So if I plug in 0 here and I plug in K here, that means that I can move this term to the other side and do a little rearranging, and I get that the standard Gibbs free energy change is going to equal negative RT ln K. This means that I can find the standard Gibbs free energy change if I know the K value for the reaction really quickly, okay? It also means that if I knew the Gibbs free energy change and I wanted to know K, I would be able to just rearrange this equation and plug it into here to be able to get K. Now remember that this is an exponential thing, so we have to be careful with our significant figures here. If we mess those up, they're going to really get any kind of errors we have is going to get exponentiated through this, and we're going to wind up with it changing things quite a bit. Again, I suggest that you calculate this term separately and then plug it into this function. Do not forget your negative sign. All right. Again, this provides a useful link between these two essential thermodynamic properties. So it can also give us information about the composition of the equilibrium mixture. Okay, we already saw this with K, but now we can kind of relate that to delta G. So if I have a standard Gibbs free energy change that is negative, that means that the products are going to be more abundant. If I had one that was positive, that means the reactants are going to be more abundant once it reaches equilibrium. And if I had the reactants and products being comparably abundant, right, so that the numerator and denominator was roughly equal in our K value here, we got a K value of 1, that would relate to a standard Gibbs free energy change of close to 0. And we can actually picture that all here, where we see that if we had a reaction process, the point where it's actually going to stop and be at equilibrium, okay, and we're going to see where we're going to, whether we're going to have mostly products or mostly reactants, is actually found by minimizing the Gibbs free energy. So the value that gives you the lowest Gibbs free energy is going to be the equilibrium point. And then if I trace that bottom of that curve down, here I would have the K that I would be getting. All right, so I'm graphing Q as I go along. I get to a point where Q is equal to K. I know I'm at equilibrium, and that happens to be the minimum Gibbs free energy. And so you can see that when delta G is less than 0, you get a situation where it favors the products. When delta G is greater than 0, we're going to get a situation that's going to favor the reactants. And when they're roughly equal, we wind up something that looks a lot like a parabola. And we're going to see that that K is going to be right in the middle. And we're going to have fairly equal mixture of reactants and products.